This here is a part I made on my CNC mill. And in this video, we will discuss everything you need to know in order to start machining your own parts. This video is sponsored by PCBWay. More on that later. Before any machining can begin, I first have to design my part, and that process typically starts in a CAD program. At its core, CAD revolves around two primary actions, extrusion and subtraction. I'll begin by sketching the basic outline of the part I want to create. Once the sketch is complete, I extrude it, transforming the 2D drawing into a 3D object. From there, I can add additional sketches on any surface and subtract material to carve out the exact shape I need. Before you machine something, especially an assembly part, it is important to validate the design. In my case, a quick 3D printed prototype can help me gauge if my design has any apparent flaws. Now that I know my design doesn't have any obvious flaws, it's time to start milling. In most cases, the stock material comes in either a rectangular or cylindrical shape and must always be larger than the part you're machining. Here is my stock. The nominal dimensions are 10 inches by 2 inches by 1 inch. I say nominal because when I actually measure the part, it isn't exactly those measurements. As you can see, instead of the advertised 1 inch, it's closer to 1.0125 inch. The discrepancy between the vendor reported and actual dimensions occur because the stock isn't manufactured to be perfect. It's just close enough. Since it's going to be machined out anyway, stock is produced quickly and cost effectively. Okay, we now know that when we buy our stock, the dimensions might be all over the place, so why is that important? It's important because when we place our stock inside our mill, it causes things to be unaligned, right? And if we're programming something expecting our stock to be exactly how we have it in our CAD, that creates some issues because they don't line up. And this can result in a part that is slightly crooked. And so in order to solve this issue, we do something called facing. Facing is a process where we cut a slight layer of the top face, and that flat face we use as a reference. So before I can start explaining what facing is exactly and referencing our stock, I need to first explain workholding, or more specifically, my vise. This is a vise. Essentially, it's a large, heavy, and precise clamp. Initially, I thought I could save money by using an old cheap vise I had, but quickly realized that was a bad idea. For reference, my old vise maybe cost me $60, but this one here, it costs around $400, $500, which is crazy and a little annoying. A milling vise is different from a standard vise in two key ways. First, when it clamps on an object, it pushes down rather than up, ensuring the part stays securely in place. Second, a milling vise can be used to reference an axis. By this I mean that when I place a part here, I can be certain that one edge is parallel to the x-axis of my machine. To make sure the vise is perfectly aligned with the x-axis, I use these 4 clamping points. And by lining things up and then using this edge finder, I can then tap in the final fine-tuning of the position. Once the vise is leveled, I can secure my stock. And once I level the vise, in most cases, I don't really have to touch it for quite a while. But if you notice something, the depth of the vise is more than my part. So when I place it inside, it just falls through. And that is an issue. To overcome this issue, we use something called parallels. Parallels are basically these thin metal pieces that we place on the sides of our vise to keep our stock offset a little. These parallels are perfectly made so that they are completely accurate and straight. This allows me to just place the stock on top. It elevates the stock to where a minimal amount of material is held down and I can cut the rest that is protruding on top. With the vise prepared and the stock in place, we're ready to move on to the next step. Tooling. A CNC mill is powerful, but it is also not very smart. We have to manually tell it not only which tool it's using, but the exact dimensions of that tool. For reference, I typically use 3 main types of end mills: a square end mill, a chamfer end mill, and an engraving end mill. The square end mill cuts in a straight square pattern, and it will likely be your go-to tool. Chamfer end mill, in my case, creates a 45-degree chamfered edge that makes it so that I can touch the part and not get any cuts. Lastly, the engraving end mill is for making light detail markings. There are also other options like a ball end mill, which is used for creating smooth curved surfaces. End mills vary in both diameter and length. Generally, the larger the diameter, the longer the end mill could be. Smaller diameters need shorter lengths to prevent snapping under load. Another key consideration is the material of the end mill. High-speed steel, or HSS, end mills are the most affordable option and work well, but they need to be run at a slower speed. If you're looking for more durability and efficiency, carbide end mills are what you want. Personally, I use the uncoated ones to save costs, but there are coated variants that last long, especially if you're running jobs continuously. The coatings help extend tool life, making them a better investment for high volume work. Since I only run occasional jobs, the uncoated ones suit me just fine. If all this information is a little too much for you, then something that you might be interested in is PCBWay. PCBWay is a sponsor of this video, and they graciously provided some parts for me to demonstrate. Even now that I've been machining for about a year, there are still a lot of mistakes I made, and it still takes quite a bit of time for me to get the part that I need. Right? There are hours of programming, and then hours of milling, and even then I have to repeat it if something comes out wrong. But with PCBWay, they offer services where I just place in my part that I made on my CAD program, I tell them what I want, and later on in the mail I receive my part. Right? And they offer services like 3D printing, CNC milling, and even plasma cutting. Right? Personally, I rely a lot on their CNC milling to save time. I'm currently a full-time student, and so having the ability to place an order, be able to do my finals and have the parts ready by the end of it is a great help. Thanks again PCBWay for sponsoring this video. Please check them out in the description down below. Alright, now it's time to start programming the mill. While CNC milling and 3D printing both use G-code as their programming languages, the user experience is very different between the two. 3D printing is quite user-friendly. You simply import your STL model into a slicer, and in most cases you're ready to print with minimal setup. Unfortunately, CNC machines don't have the same convenience. To program a CNC part, I need to use a process called CAM. Unlike 3D printing, which adds material layer by layer, milling removes material. With CAM, I have to manually define where and how I want the machine to cut. It's much more hands-on because every cut, every toolpath, and every parameter must be carefully planned. There are plenty of YouTube videos for more in-depth detail, but here's a quick overview of how I program my part personally. Most of my workflow revolves around SolidWorks and Fusion 360, and I know Fusion 360 works well with Tormod, so that has been my choice of CAM software for about a year now. So this here is the software. So the first step when beginning it is to make sure you are in the manufacturer settings, and we start by clicking New Setup. This allows us to give the program the dimensions of our stock. In most cases, your stock will probably be around the same size as your part, since it doesn't make sense to use a huge plate to cut out small millimeter parts. The stock I will be using is this. Right? We measured it previously, and so just go ahead and do that again and then put those values into the program. In the upper right hand corner, this page opens up, and then we click over to the stock settings. We can choose the dimensions of the box. So we'll go ahead and measure this again. The width of it is 51.38. The thickness of it, or the height, is 25.7. And the width, or the length, is about 10 inches, but for now I'll leave it at 230. The last step we need to tell the program about our stock is where in the stock our part will be located. If we look at the side profile, you can see that it is dead center on all sides. Some cases it might work, but for me, I need it to be a bit closer to the top. So I will edit that, see offset, and only offset about 0.5. The reason being is when I place this stock into the vise, I need to make sure there's enough space for the vise to grip onto. If you look closely in the video, the stock leaves about 1/8 of an inch where it needs to grab on. 1/8 of an inch is about 3 something millimeters. Over here I have about 5 millimeters. I gave it some room since later on I need to input the measurements of my end mill, the actual part that cuts, and sometimes that measurement is off by a little bit. I do not want it to cut into my vise. With that, the final step is to tell it where the origin point is. I tend to choose the bottom left corner. Reason being is later on we need to tell the machine where the origin point is on the actual stock. And it's a lot easier to locate on a corner than somewhere in the middle where there's nothing for it to touch. There are other settings, but for the most part, I just leave one done. And with that, our stock is done. Now that our stock settings are set, the next step is to start actually cutting. If we look up here, these are the options we can go through for cutting or anything else we need to do. In most cases, I stick to the 2D area, with the first step always being facing. If you look at the stock, it's very dirty. It's a little bumpy, a little scratchy, and it's not perfect at all, right? I do not want my part having this surface on it. So in order to overcome this issue, we do facing. Facing is the process of cutting off the first few layers of a part and making sure it's flat and even. In the extreme cases, you want to do that on every side to make sure everything is aligned properly, so that when you cut it, you know for certain that everything will come out perfect. In my case, don't need that as much, so I'll just face the top and maybe the bottom. Once I select the option of facing, I'm again greeted with the same panel. The first thing to select is the tool. In most cases, your tool probably won't show up on here, so you'll have to input the information on your own. In most cases, the company where you purchase your tools from will have all the information there, or it'll be on the actual package of the tool you buy. In my case, Tormach offers some options, and one of them does happen to be the tool I use. If your tool doesn't happen to be here, there's an option to create one, and when you create one, this panel will open up. You can provide a name, and here is where you would input the information. You determine the type of end mill it is. In this case, for facing, you'll more than likely use a flat end mill. The next parameter will be the number of flutes. This is the amount of cutting edges. So you see these twisting bits here. In most cases, for softer materials like aluminum, 2 to 3 flutes are great. For stronger materials, you would want to move up to 4 flutes. The reason being is the less flutes there are, the more brittle it is, because there's less material there. And so when you're ramming it in, it might snap. One of the options is high-speed steel, which is still a very usable material, and I use it in some of my bits. But if you want to buy an end bit and use it for a while and not have to track things at first, carbide is the way to go. It's not that much more expensive and allows you to push your machine a lot faster. So when you're getting to the trial and error phase, might not be the worst option. Anyways, at least for this end mill, carbide is the material. And then from then on, we determine the geometry. All right, the diameter, and even tells here, diameter here is 3/8 of an inch. Same thing with the shaft, which is where it goes into the collet or the tool holder. The overall length is 2.5 inches. The length below the holder, and just basically this is the visible part, is about 1.1 inches. The shoulder length is 1 inch, and the flute length. So the flute length is actually where it cuts. Basically, anything above this, you do not want it cutting any material, and so it's about an inch. If you want to know how you measure this, you can just use a caliper. I'm sure there's more tools to get it more precise, but for the most part, that's fine. I just make sure that I don't cut anything over 0.9 of an inch, just to make sure, in case I measure things wrong. Other than that, again, information, and this is where you would input the speeds and feeds. In most cases, when you're buying these tools, the manufacturer will provide a sheet that tells you the speeds. So this is the horizontal, the vertical speeds of the actual machine, and the rotation speed of the spindle. They'll tell you that depending on the material, and that'll be a great help, but I've never been lucky. And so I've had to figure it out by trial and error, and even now I'm not too sure how it's determined. This is not professional advice, and this is just someone who has picked it up as a hobby of sorts and is still figuring it out in my free time. In general, for aluminum, you want to go at higher speeds. So this is speeds above 7,000 at least. For steel, I would be lower, but I've never really machined steel. And so most of my experience has been with aluminum. Luckily, Fusion 360 has a formula. So all I do is input the spindle speed and it'll figure out the the horizontal and vertical speeds for me. So we see here, the one they recommend for this spindle is an RPM close to 7,600. Once everything has been inputted, I accept. And now my tool's set. Depending on your machine, you can have coolant. Basically, when the spindle is cutting metal, things heat up, right? The part might heat up a little bit over time. In most cases, you don't want that since that does warp metal, or the end mill actually gets kind of hot. So you shoot it with a specific type of liquid called coolant. This coolant makes it so that the metal does not erode and is just washed out in the end. Once our tool parameters have been set, the next option that comes up is the geometry. In this case, since we chose facing, it understands that we only want it to cut to a certain depth. And since we already told it the top of our stock, and it understands the bottom of our part, we don't need to select too many options. Since I selected 0.5 millimeters, it only drops 0.5 millimeters, which is not that deep of a cut. But for example, if I wanted to face off 5 millimeters, I could go in one pass. Some machines that might be pushing it. And so I would probably max it at 2 millimeters. And so it would do 3 passes, right? 2, 2, and then 1. For that option, you will look at multiple depths. I can tell it the maximum step down and which one the finishing step is. So if it should start at 1 millimeter or it would end at 1 millimeter. Since it's only 0.5 millimeters, I can do it in one pass. Everything else can be left as is, and that is our facing. And just to verify that we did everything correctly, we can simulate it. So we go into actions, simulate. This is the tool we have specified. When we go in it, you can see how the part will go in. Great, looks fine to me. If you're professional, don't judge me if I did something terribly wrong, but it should be good for now. With the facing out of the way, the next step is to start actually cutting out the part. The next tool I use is 2D adaptive clearing. The tool we're using will be the same one, since I do need it to be able to travel down a certain depth. This tool is a little bit different from the facing, since now we need to specify when the part we wanted to cut. For now, let's start off with the outer bounds. So if I come down here and select the bottom sort of face or the bottom perimeter, this blue is where it will be cutting. This here tells us how the end mill will move. It has identified the top of the stock as the top, which I guess in this case we could leave, but not exactly accurate, since top now is the model top. Now that we selected the bottom face for it to cut, we need to tell it how fast to cut down, right? We don't want it to go in one pass, since that is a lot of friction and could break things. And so we can choose multiple depths. We can choose a maximum depth of, I keep it around 2 millimeters. I can definitely push it more, but don't want to risk things. This is the direction. Basically, you can have it where it only cuts from right to left, or left to right, or to either. There are advantages to both. There are advantages to either one, but in my case, not too picky. I'm gonna leave it at it as is. The optimum load is again how much it cuts in. So this is the amount it cuts in from the side. Right now it's at 3.81, which I believe would be about half, but it's about its radius. Sorry, it would be about the size of its radius. I will shrink that a little bit to 3. And then stock delay. Basically, if we want to do a rough pass, basically it just goes by quickly, cuts as much material as it wants. We can leave a sort of perimeter to then go back and cut it slowly to leave a nice texture. For now, it doesn't matter to me as much. These parts are going to be more structural and actually aesthetic. And again, there's lead-ins, ramping, everything else, other settings that you can experiment with. In this case, things should be fine. So once I click OK, it'll do the calculations. And now we go back to the simulation. All right, now that the outer perimeter has been cut, the next step is to follow a similar process for the internals. You will see that it'll start creating a helical pattern before it plunges in. This offloads some stress and make sure that we keep things well maintained. Okay, that is the basic idea. I could elaborate further, but covering every single point of this will take an astronomical amount of time. You're probably better off looking through other videos, right? Hopefully this video can provide you with some terminology and some aspects to look into. Now that I've explained some aspects of it, there's a lot of repetition, right? The same process goes through with holes. And so come back in a bit after the parts are done. Okay, I went through and finished the part. The inner pockets, the outer cutting. Went back in to clean my pockets since they weren't perfect. Milled out the holes and milled out those as well. The one new step is the chamfer. Basically, this is an option up here as well, where all I do is select the edges of where I want it to be cut. Select the proper tool. In this case, it is a 1/4 inch 90-degree chamfer. Sorry, 1/4 inch 45-degree chamfer. And the only setting I really changed came to here. Chamfer with 1 millimeter, chamfer tip opposite. Now that I have my part programmed, the next step would be to export it. To export it, it's similar. It's up here in the setup section. Create an NC program, right? We make sure we select the proper options. In this case, I want everything selected in my setup too. And other than that, we specify a post. So this basically tells us the language that the machine runs or how it's set up. In this case, it's in Tormach. I designate the name, part. You just call it YouTube part for now. So it's an output folder. And in my case, I put it onto a USB drive. I upload it to my Tormach behind me. Make sure I export as an NC program. And I click post. Should show on my desktop or in my flash drive. And it's ready to be uploaded to the machine. With the program on my flash drive, it's now time to head over to the machine. In my case, I'll be demoing all this on my Tormach 440. But depending on what machine you have, things will differ. Be it either a Haas mill or a 3D printed one. Here on the right side is the power switch, and here is the e-stop. Basically, this is a button you press whenever something's about to go wrong. Now, I clear the console. The next step would be to reference my axis. We do this because the machine needs to know where it is located in 3D space, and so this allows it to do that. Right here are the parallels I'll be using. These will leave me about 1/8 of an inch to grab onto my stock, and I'll be grabbing my first end mill, which will be a 3/8 inch, 1 inch long carbide end mill. We're placing them to the sides, make sure they're clean and there's no material on there, or else that will mess up the alignment. The stock I've chosen is about 2 inches by 1 inch by 9 inches. This is close to the max the machine can do when it comes to the max length of 10 inches on the y-axis. I place it in my stock and make sure it's securely inside. The next step is to start locating my origin point. Right, this is done by using a automatic probe. Most mills have something like this. It might look different, it might have different features, but the basic idea is to use it as a locator. The bottom tip of it is a sensor, and it'll return a value whenever it hits something. In my case, if I want to locate the upper Z height, I will position it about 1 inch or 1/2 inch off the top face in the middle. It will slowly go down until it touches something, and it'll return back to me the value and save it. Similar process is done with the most left side and most closest side. Right, the panel is pretty self-explanatory. It has images for all this, and once the button's pressed, it'll automatically find you the top or find you the corner and return the value. In some cases, you might not have a sharp corner left, and so there are options for finding inner corners or even location of a center hole. Right, and I've used this before. You have located your starting point. The next step is to insert a proper tool. For Tormach, at least, the process looks about inserting tool with one hand and holding the top with the other, tightening it to make sure that the tool will not fall out when in use. Before starting up your machine, you might want to make sure that the area is clean, make sure it's not going to hit anything. You want to make sure that there is enough oil in the machine, just like any other proper tool. You will want to make sure the coolant nozzle is in the right direction. I've forgotten about this and splashed it all over the back wall of my room. The next step is to load the G-code. You go to the location of your flash drive, you load the file onto the actual machine, and then you load it into the console. When open, it'll show you a brief preview of what part you are milling. Make sure it's the correct one, and make sure the origin point is in the same location that you have set. You will want to double check the tools, right? It'll give you a list of tool numbers. Make sure the tool heights are inserted. And with that, you can cycle start. The machine is not programmed to detect errors. You will have to do that yourself. You'll have to get accustomed to listening to it and making sure it sounds proper. And also, pay attention to it from time to time to make sure things are good. If you're wondering how you handle tool changing, the machine should stop on your own and give you time to change it. It'll just stop and will continue until you press start again. And from then on, you do a similar process. You take out the tool, put in a new tool, hit go. And since you set the origin point, everything's already calibrated in. All that is left to do is just watch and see it cut. Like 8 or 9 o'clock, so hopefully no one gets mad at the sound. Okay, so some bad news. Well, actually, first some good news. Machine out of part. Finally getting back to work on this piece of shit. Some bad news though. If you look here, it's messed up. What happened was one of the drill bits I was using, or sorry, TTS holder, whatever it's called, came undone. It seems that this piece is not suitable. This is not the first time this has happened either, which is a bummer. After hours of programming my part and more hours of watching it machine and having to make sure everything's fine, I finally got my part. I tested it on my robot, it fit, and there are some blemishes, and I definitely could have made it better, but it's perfect for what I need. When I machined the part, the top area was done, right? But I was still left with the bottom perimeter. In order to get rid of that, I had to take it out of the vise, flip it upside down, and clamp onto these bottom edges. From then on, I did a facing operation where I just kept going until the top layer was gone. And once I was left with this flat area, I could locate with one of the holes and then create programming to add in the chamfer and add in any other holes that I was missing. So with my part done, the next major question to ask is if it was worth it, right? This was only one part out of probably the 20 parts I need on my robot. And so if this part took me, say, 8 hours, is it worth to spend, what would that be, 160 hours on everything? And the question is a bit complicated, right? The next parts would have definitely been quicker, right? I need duplicates of them, so I don't need to program a whole new thing. I can just chuck in a similar sized stock into my machine, and as long as I place the origin point in the same area, should cut out another part within a short amount of time. The complexity comes when I need a different part machined every time, because then I have to program it again and repeat the whole process. So this adds up. The machine doesn't have to be watched all the time. When it's running, it'll go through the whole process. As long as it makes sure the drill bits are fine, things should go well. But for people who don't want to spend thousands of dollars on a machine or even go through the process of learning all this, there are alternatives, right? One of them being a service provider, like the sponsor of this video, PCBWay. So these are some parts I had ordered from PCBWay. If you look closely, it look different than what I made. That's because there has been some surface treatment on this. It's a lot smoother. It looks nicer in some regard. I do like seeing the cutting patterns on my part, but this is also great too. They are just as strong. They are probably more accurate than what I did since they are done by actual specialists. And the prices, although I could definitely make it cheaper, it saved me a ton of time. Right, from the time that I placed an order and the time I received it was about, I think, less than 2 weeks, which was great. Didn't even have to pay for faster shipping. That was just standard. While they were making it and shipping it, I was doing my finals. Right, there was a period of time that I could not do anything since I had a priority in something else. And so this service worked out great for me. I purchased my machine since I do enjoy prototyping, testing things, but not all my projects require me having something like that, right? A lot of things can be done by just ordering them online, and they'll definitely save me a lot of money. So it really depends on what project you're doing and the person as a whole. But whatever your situation is, both options are reasonable, and both options lead to the same thing, creating something that is pretty cool. That's it for this video. I know that I probably skipped a lot of things. The original recordings were about 3-4 hours long. I had to trim a lot. It was hard to figure out what to include and what to cut. There are a lot of different nuances to consider. There's a lot more I could have gone in with the speed feeds, a lot more I could have gone in with referencing and with making sure things are aligned well. Machining is a bit of an art. It has to be pretty perfect, and that requires time and that requires a lot of explanation. But this is just a crash course. If you're still here, I recommend visiting other channels to fill in the gaps. From memory, the channels that come to mind are NYC CNC, Titans of CNC, and other smaller channels. When I was first learning this, I definitely was on YouTube quite a bit, trying to figure things out, because the last thing I wanted to do was break my machine. It's a learning process. It is a big endeavor, right? You can give it minimal time and get, 95% of the way there. That is fine for most projects, but if you really want to nail it down, it'll take time, just like anything.